Okay, so we're on page 33, and like I said already, we're going to talk about interference and diffraction. They're related. We want to talk a little bit about both concepts in physics 20, but very minorly, and it's about mechanical waves we talked about, not about electromagnetic radiation, but it's very similar circumstances. So the four outcomes that we're going to cover in the lesson are describe qualitatively diffraction and interference. Okay, so that means define them. Like actually talk about what they are. Can you guys not talk while I'm talking? It's pretty rude. Describe qualitatively how the results of Young's double-slit experiment support the wave model of light. So again, that's describe. Solve double-slit and diffraction grading problems using one of those two formulas. And that's a bit of a double-edged sword, that one, in terms of what we have to do with those formulas. And compare and contrast the visible spectra produced by diffraction gratings and triangular prisms. So contrast is green, but compare is blue. What you actually have to be able to do to show me that you can meet those outcomes is the following list. Define diffraction, so that's yellow. State that diffraction provides evidence that supports the wave nature. That is yellow as well. That standard of excellence question is blue. So that's evaluate properties of reflection, refraction, diffraction, and polarization in terms of support for the wave model. So that's blue. State that the result of the double-slit experiment is an interference pattern. That's yellow. Standard of excellence, so blue. Explain interference in terms of the principle of superposition. State that the results of the double-slit experiment support the wave nature of light, so that's yellow. Observe visible spectrum created by diffraction grading. Well, you've already done that. We'll call that yellow as well. Calculate any variable in either of those equations. So lambda is equal to xt divided by nl, or lambda is equal to d sine theta over n, assuming a small angle approximation to be valid. And that will make more sense once we actually talk about that, what I mean by small angle approximation. So that's green. Observe visible spectra produced by a prism. We haven't done that yet, and we will. That's just a lot harder to do. But we'll look at that on Monday. State the order of visible light by wavelength or frequency and by color. So it's Roy G. Bibb. State that blue is more affected by refraction, and state that red is more affected by diffraction. So those are all yellow. So this is sort of, there's a lot of theory in this particular concept. So in terms of what we've done so far, there's a lot of theory in the first thing when we're just talking about electromagnetic radiation, introducing you to the concept. There's a lot of theory in this, and then what we're going to do on Tuesday, which is polarization, there's then also a lot of theory. Everything else tends to be kind of calculation stuff. Okay. And I think we start on the next page. So we're done with the highlighters. Okay, so in terms of history, and this is going back pretty far, there have been three different models have been used to explain what light is, like what EMR is, like whether it's a particle, whether it's a wave, what it is. And there's been a lot of argument, a lot of discussion, a lot of conflicting views and experiments performed over the centuries to try and prove one or the other. So the first sort of notion of what EMR is a particle theory of light. And that was really supported by Isaac Newton. Sorry, Sir Isaac Newton is a bit of a turd, but he had a really, really horrible personality. Oh, he's just a dickhead. Like he, complete utter dickhead. Like, and that comes like right from, like Stephen Hawking said that. Like, what's the quote from Stephen Hawking? It's like, it's actually quite funny. But so there's two people, and I can't remember the name of the guy who actually did it. But there's two people credited with inventing calculus. And Newton basically drove the other guy who actually invented it to his grave, and then made sure nobody went to his funeral. So, bit of a dick. Yeah. Okay, so this is from Brief History of Time. Isaac Newton was not a pleasant man. His relations with other academics were notorious, with most of his later life spent embroiled in heated disputes. Following publication of Principia Mathematica, surely the most influential book ever written in physics, Newton had risen rapidly into public prominence. Blah, 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 blah. Where's the thing? That's here. Leibniz is the other guy who invented calculus. He basically kind of kept him out of the Royal Society of Science and kind of stuff like that, and made sure they went to his funeral. But yeah, that's corroborated by a lot of other people. He just wasn't a pleasant person. But having said that, because he had a lot of notoriety in terms of his laws of motion and the universal law of gravitation, he believed that light is a particle, that light traveled as a particle, behaved as a particle, and all that. And so the majority of the physics world and science world supported him in that. It was a very simplistic model, but it was the more popular model, and I think that's because it was attached to Einstein, or to Newton. And so what that particle model says is that electromagnetic radiation is a stream of tiny particles. Each particle has a mass, has momentum, and has the ability to be electrically charged. Okay. Then there's the wave model, which was put forth by Christian Huygens in about the 1600s. And he said that EMR is a stream of transverse waves. But unlike water waves, EMR doesn't require medium to travel through. It can travel through a vacuum, it can travel through air. Doesn't have to actually have something that it travels through. We know that part is actually true because EMR travels through space, and there is no atmosphere in space, so there is no medium there for it to travel through. The wave model is what became popular after a guy named Thomas Young performed what's called a double slit experiment, which is probably the granddaddy of all sort of physics experiments. It's the experiment that everything kind of goes back to. In a lot of physics. And that showed that when a beam of light is shone through two slits, it results in what's called an interference pattern. Okay? And an interference pattern, we can make it with waves. It's where you might have a wave moving like this and a wave moving like this. And when they start to kind of go together, like when they reach a point where they're combining, where crest and crest meet, right, they get bigger, and where trough and trough meet, they get smaller. And we talked about that in terms of standing waves in physics 20, when you kind of make that, when you can make that with a slinky, when it looks like the nodes are just going up and down on their own. Okay, so because of Young's double slit experiment, that was pretty much definitive proof that light is a wave, not a particle, because particles don't interfere. Okay, you can't get, or at the time it was thought particles couldn't interfere. You can't get it, like you can't shoot tennis balls through two holes and have an interference pattern. But you can shoot waves through two holes and have an interference pattern. And let me see if actually I can kind of show a little video to explain that a bit. I don't know if it'll do anything other than. I'll get my technology ability improved eventually. Okay. Okay, so there is stuff in here that is getting a little further ahead than where we want to be, but it is what we're going to talk about the next couple of units. So it is everything in here is sort of relevant to physics 30. But it shows what an interference pattern is, and it's really well done.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands.
Okay, so I just want to stop there because what's coming next is not part of this unit, but it's looking forward to what we're doing. But basically, what happens with light is that in order for light to be a particle, it would have to show the pattern like that the tennis ball showed, right? With just if you shone light through it, there would just be kind of single lines on the screen behind that line up with the slits. Okay. But when Thomas Young did his actual experiment, he got an interference pattern. So he got something like this, which indicated that that light is indeed a wave. The next part of this is kind of something that kind of got thrown into everything and just confused the crap out of everybody, and it kind of knocked physics on its butt, because at this point, by the time Thomas Young discovered that experiment, or did that experiment, I think like late 1800s or so, early 1800s, late 1800s, I can't exactly remember. Everybody assumed that everything there was to know about physics was known. Right. That all then changed kind of at the turn of the 20th century with the next experiment that's in here. And that has kind of allowed for us to have things like iPods and GPS and cell phones and a lot of the newer technology that we take for granted. And it's got us on the verge of having what's called a quantum computer, which would make these computers look like the first original big giant computer that took up an entire room.
Good so far. Now, let's go quantum.
So that just means really small. Quantum means really small.
An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit, see which one it went through, and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave functions simply by observing.
So, and that is probably still, like, pretty much not explained well in physics. Nobody really has a solid idea of why that happens. They just know it is happening. Okay, and so then things we can, it's sort of, there's a lot of stuff in history in terms of science that talks about how technologies came along before the science was understood. And it was through those technologies that more of the science was understood. And that's really what's going on with quantum physics, which I'm getting quite ahead of myself here, because that's sort of getting into our next two units. But we can build technology based on the fact that electrons do that, but we still, as a physics community, have absolutely no idea why that happens. None whatsoever. Okay, and there's about 4 basic different competing schools of thought on that, and it is not pleasant when those arguments about that occur. So, but we'll talk about that a little bit more when we get further into the course. But what that meant then, the part of that I really wanted you to get was the interference pattern with the wave. So when you shine light through those double slits, you get an interference pattern. And you guys are seeing that, but you're seeing it, like that's not monochromatic light, right? That's light, that's white light, that's a combination of Roy G. Biv. If I actually use like a kind of something a little bit simpler, well, it's a diffraction rate, it's like what's in your glasses, but then I use a laser, which is monochromatic light. There you go. It's hard to see, but you should be able to see a really bright spot in the middle and 2 lighter spots kind of on either side of it. That's an interference pattern there, and I might be able to get, I think I can get another dot out of that. And there's the blue one, the purple one, but it's a little bit lighter on the side of the green. That's sort of basically what's going on, except this is way more than 2 slits, but this is an interference pattern. So that's, the waves are interfering with each other, and where crest meets crest is where you get a bright spot. It's brightest right in the middle, and then you get bright spots kind of going out at regular intervals on either side. That proved rather definitively that light is a wave. Okay, so that made the wave model of light then replaced Newton's particle model of light. Okay, and 3 very specific concepts or investigations or experiments led to that rejection of light being a particle and instead being a wave. And that's Huygens principle, Young's double slit experiment, which was talked about in the video, which I've mentioned already, and we'll talk about in a little bit more detail. And then just the invention of diffraction gratings, which is what's in those glasses. Okay. So the first thing we want to talk about is Huygens principle. And what Huygens principle basically says is that a wavefront, whether it's water waves or light waves, it's made up of every single wavefront. So when you get a single wavefront like this, that's actually made up of a whole bunch of smaller wavefronts. And then each of those smaller wavefronts is made up of even smaller wavefronts. And then you can kind of keep splitting them up indefinitely. So wavefront is made up of tinier wavefronts, and the process repeats. Every point on the wavefront is now a source of secondary waves. And each wavelet spreads out on its own, and then that allows the wave to keep propagating outwards. And if you were to draw a line, like where the wavefront is, it forms a tangent line with the actual kind of line of the wavelets. And here, I just want to get the diagram here. Okay, so whenever we have that's the source of our wave, so maybe it's a light or something like that. So like that light, we can use that as a source of our waves. So the perspective on this is a little bit off, but I'm going to... Okay. My dad taught me how to draw light bulbs when I was little by saying, draw what looks like a lady bending over pulling up her girdle. Took a while there, right? Okay, so this is like some sort of wave source. That's what I have here. This is a wave source. Okay. And now, with a wave source like a light bulb, the waves are actually going out on all sides of it, right? It's 360 degrees around, but I'm just showing on one side that light coming out. So we might see kind of light comes off as a wave. So we've got sort of that initial wave. What Hugin's principle says is that initial wave actually has, it's not just one sort of wave front, it has a whole bunch of tiny little wavelets on it. So we could draw in little, like, kind of smaller waves on here that sort of, what that does is that propagates the wave outwards, like this. So then the wave moves outwards. And we can think of this here then as being another wave front. But what we want to do is think of each of these as sort of little wavelets that make up that wave front. So the green are little wavelets that make up the wave front. And then, you know, from there, that can kind of continue. What we basically have is each of these little wavelets has tiny little wave fronts on it, right? So then they would all propagate outward here. And it just keeps going. And I'm not going to draw another level on here, but we could do the same thing. Right? Each of these has little wavelets, or each of these little wave fronts has little wavelets on them, and it would just kind of keep going. And that's sort of what what allows that, or that's what Hugin said allows that wave to keep propagating outwards. So he's not really saying the wave is like tiny little particles, but he's saying like one big wave can kind of be broken up into a whole bunch of little tiny wavelets. And we can kind of think about it as not just one big wave, but as a whole bunch of tiny little wavelets, but they're all still waves. Okay, and so then no? You can't record what it's okay. Okay, so then the next so that was sort of the first thing, and that wasn't really an experiment or anything. That was just a theory. Like, that's just something he said. Like, I believe this is what waves do, it's sort of it's held on, but it's not really anything that can be proven or disproven by an experiment. It's just a way of thinking about waves. The next thing we want to talk about is Young's double slit experiment, and there's a history to this because Young wasn't the first one to try this experiment because it was recognized that if waves, when they went through double slits, interfered, that would be a definitive way of proving whether light is a particle or a wave, because if you can get light to go through double slits and give you an interference pattern, then clearly it's a wave, not a particle. Okay? And so scientists have been trying that for years, for a long, long time. So many scientists have been working on trying to observe an interference pattern for light, but they were unsuccessful. Okay? Because they were unsuccessful, they assumed that that meant that light was a particle. The problem was that Thomas Young looked at sort of these experiments, or sort of the results of these experiments that scientists have been doing, and he came up with ways of fixing the problems that those previous scientists had in order to make that interference pattern. One thing that was wrong is that in order to have an interference pattern, you basically need a wave source that's in phase. In phase means crests are happening at the same time and troughs are happening at the same time. So you can get waves that are in phase by having like a single slit to start with. So you've got just a single slit, and then you have a screen with double slits. I didn't line that up very well. This should be kind of in the middle here. And what you do then, because you're trying to get two waves that are in phase with each other. And in order to do that, what you have to do is send them through the single slit first. So he would send a wave through the single slit, and so then only certain kind of waves would go through. But then what he ends up with is waves that are in phase. So the crests are happening at the same time when they come through here, and the troughs are happening at the same time. So the scientists who were experimenting before did not have waves that were in phase. They were just using sunlight or something like that, or they were using, or like, it wouldn't have been light bulbs, but it might have been two candles with flames. And there's no way of getting those, the light from those candles to be in phase, the waves from the light from those candles to be in phase. So he started, Thomas Young started with monochromatic light, which is light of a single color, and a screen with two slits in it. He needed the light rays to be parallel in phase, which is what I just described. So he shone a single light source through a single opening first, like a little pinhole, and then the single beam hit the double slits, and so then he got two waves that were in phase. And what he saw provided evidence that light was a wave, because he saw an interference pattern. And so the difference here, like what he would have seen if light was a particle, he would have saw the monochromatic light, it's all coming through and it's all in phase going through two slits. Would have been just like if you had like a picket fence and you had a board behind it and you spray painted in front of the picket fence, right? The spray paint, some of it would hit the picket fence, and what didn't hit the picket fence would go through the back and just form two lines kind of behind it. And so that's what he should have seen if light was a particle, because only some particles would pass through here, right? Like only the particles that lined up directly with the slits would actually pass through. Anything that just hit the wall part of that that double slit apparatus would not go through. So you would only get a pattern on here from the light that actually made it through the slits. Okay. What he did actually see was an interference pattern. He got the series of bright lines, bright spots and dark spots on a screen. So as soon as the two light rays go through the slits, they start to diffract. Okay. Diffract means they bend around corners. Okay, that's what diffraction is, bends around corners. So what diffraction is that it's when those waves go through that slit, and instead of it just being the wave that's in front, that actually portion of the wave that goes through the slit, the wave actually bends to fill in the spot where no wave went through. That's diffraction. That's that kind of bending around corners, like waves bending around corners. It's why we can hear radio from so far away. Again, in like AM, we can hear from a lot further away than FM, because AM radio diffracts a lot better. And since at the time it was believed that only waves diffract, not particles, this experiment of Thomas Young's provided the evidence needed to actually state that light is indeed a wave, not a particle. So, here, I've got the stuff about diffraction here. So this is just sort of the definition of diffraction. It's the bending of a wave not due to reflection or refraction. the waves change shape and direction when they encounter a small opening or a barrier, so they change their shape or which way they're going. They appear to fill in the missing spots. Longer wavelengths diffract more, smaller wavelengths refract more. So longer wavelengths, so this means that red diffracts more. And blue or violet, I'll say blue or violet, like at the other end, refracts more. I can illustrate that pretty simply, somewhat simply, but if I look at the fact that that's a red laser and I shine it through my diffraction grating, if I look at where the second set of bright lines shows up, so it looks like there's almost a foot between the bright center and the ones on the other side. And now without changing my position, I'm going to put light with a smaller wavelength through. That's the green, and they're closer together. And the purple, which is even closer together. The water, oh my, okay. So, and I've kind of already talked about this, but diffraction is like when water waves go through a slit, they spread out, okay, and they make a wave that's wider than the opening. I'm going to be talking about. So they fill in the missing area behind the obstacle, so it looks like there wasn't ever an obstacle. So if you have, it doesn't have to be a slit, it can just be a barrier. We have waves going past a barrier. They'll go past it, they'll fill in the spot on the other side that the waves couldn't get around. That's diffraction. This is something that's quite key. Okay. In order to see diffraction happening, so and from that, in order to see an interference pattern, the opening, the size of the opening, can't be any, like it has to be about the same size as the wavelength of the wave. And so in that video we watched, we'll talk about eventually, but one of the reasons why viewing the electron made it not go through as a wave, it collapsed the system, made it go through as a particle, is not because it knew it was being watched, but it's because the wavelength of light is significantly bigger than the wavelength of an electron. And so when that light hits the electron, because that wavelength is bigger, it actually changes the position of the electron. It changes the position of the information about the electron. And that's why we can't look at small things like particles in a microscope, because we're looking at them with visible light, and visible light has a much larger wavelength than electrons. Okay, and then I've already mentioned that here, there are two longer wavelengths, red diffract more. Okay, the actual interference pattern and the terminology go along with the interference pattern. This is, there's no real significance to the colors on there. It's just using colors to kind of illustrate the different lines, but it's actually not even terribly physically correct in terms of what the colors are. But this is an interference pattern where the center one, the 0, is the brightest spot. Okay, so that's the central antinode. It's the center of the pattern, and it's the brightest antinode. Constructive interference is where crest meets crest. Okay, and waves making it to the screen, well, those waves that make it to the screen where crest meets crest are going to make bright fringes, which are called antinodes. So the things that are numbered are all the antinodes. Okay. So these are all antinodes. And that is where, like I said, crest and crest meet. Destructive interference is where crest meets trough, and it's where the wave cancels out, it disappears. And you get dark fringes, or what are called nodal lines, and that's the spaces in between. So the spaces in between are called the nodes, or nodal lines. So the bright spots are the antinodes, the dark spots where there is no light are the nodes, which to me always seems backwards, but that's the terminology that was developed. One thing that we did with the springs last year to kind of show constructive and destructive interference is when they were on the floor with the slinky and you both sent a pulse on the same side of the slinky, and where they met, the pulse got bigger. And when each person said, one person sent a pulse on this side and one person sent a pulse on this side, where they met, the slinky just flattened out. That's the same thing. It's the same idea, but with a much cruder device than light. Okay, so mathematical analysis here. Okay, there's two formulas that we're going to learn, and we're probably only going to make it through the first one today, but we'll see. So n is the number of bright fringes that you are away from the central antinode. So if we go back actually to this page over here, these numbers down here on the bottom, that's n. Okay. So in the center, n is 0. Then the first one on either side is 1. The second one is 2. Third one is 3, and so on. 4. Okay. So the formula is this is the easier formula. It's lambda equals d times sine theta divided by n. Okay, we said n is how many bright fringes you are away from the central fringe. Lambda is the wavelength of the light. D is the distance between the slits on the diffraction grating. Okay, so that's in meters. Lambda's in meters. And I've got what that is. And theta, it's the angle between the central fringe, or central antinode, and the nth antinode, so the antinode that you're looking at or using in the problem. And so if I draw kind of a diagram to represent this, so what I have here, this is my screen where the pattern will show up. Okay, and this is my slit screen. So to keep them apart, we'll call this the viewing screen and the slit screen. The distance here between the slits, that's d. Okay, so that's how far apart the slits are, that's d. And then if I have fringes, so that would be my central fringe, so that's n equals 0. Then I might have slightly less bright ones on either side. They're both n equals 1. And the same distance away, I'd have n equals 2, n equals 2. Same distance away, n equals 3, n equals 3, and so on. So that lambda is if I drew an imaginary line from the very center here, not from the slits, but from the center, like I'm basically going from this central bright spot, a line straight across, and then let's say I'm investigating n equals 3, and I draw that right triangle, then lambda is the angle between those. And the angle you use, it's appropriate to whatever fringe you're using. So if you're being asked to analyze the second fringe, then n would equal 2, and the angle would be, from that triangle there, or n equals 1, or n equals 300, whatever it is. So we'll do an example using this formula, and I'll try to refer back to the diagram. If a yellow light with a wavelength of 540 nanometers shines on a double slit, but the slits cut 0.0100 millimeters apart, determine what angle you should look away from the central fringe to see the second order fringe. So we have our wavelength is 540 nanometers, which is 540 times 10 to the negative 7 meters. Our distance between the slits is 0.0100 millimeters, which is 0.0100 times 10 to the negative 3 meters. N equals 2, and we're trying to find lambda. So we would, that would mean that lambda that we're trying to find is from that triangle there where we're at the second fringe. So that's the angle that we're looking for there. Just it's a little different than my diagram, but it's the same idea. So lambda equals d sine theta over n. So lambda times n divided by d is equal to sine theta. So theta is equal to inverse sine of 540 times 10 to the negative 7 meters times 2 divided by 0.0100 times 10 to the negative 3 meters. And you want to make sure you're in degree mode, not radian mode. You're not getting a headache, Trev? I think it wasn't those glasses. I've got 3D glasses. I think it was Andy Beeman who wore them home. Like she walked home with them. And I don't know how she did it, because I would have been walking into traffic. It's like wearing somebody else's glasses. Did anybody get an answer? What'd you get, Koya? You should get 6.20. You didn't get that? Are you in radian mode? Oh, 0.0? That's right. You're getting it. Oh, it's negative 9. Yeah, you're right. Yeah, that's right. That should be 9. There we go. Okay, that helps. Yes, yeah, go ahead. It's probably getting pretty hot too. Okay. It's just getting it's distracting. It's hot over there. You have the Christmas lights still on. Okay. The small angle approximation is a slightly different formula. There's a lot more places to make mistakes in it. Okay, its lambda is equal to xd over nl. Where lambda is still the wavelength, and that's in meters. D is still the distance between the slits. And that's in meters. N is still the whatever fringe you're looking at, right? the order of the fringe. Okay, and that doesn't have a unit. X is the distance from the central fringe to the fringe you're investigating. That's in meters. And L is the distance between the screens. And that's in meters. So the problem here is that you've got 4 different variables that are all measured in meters, and it's really easy to confuse them. It's probably the only one that you're never going to get wrong is wavelength. But it's really easy to confuse X, T, and L, okay, in this formula. And you can see that if you confuse them, you can get the wrong answer. So I have a simple solution for that, and we'll talk about that in a minute. I want to draw a diagram to represent this, like the one I did up there. So D is still the distance between the slits. L now is the distance from between the 2 screens. Okay, so from the screen with the slits to the screen that you're viewing the pattern on, that's L. And we can still, like if this is 0, 1, 2, 3, 4, 1, whoops, 2, 3, 4, that's supposed to be a 1. Well, there's no angle in this formula, but we need to deal with an angle first before we can use it. That's why it's called the small angle approximation. So if I'm investigating fringe 3, okay, that angle in there is still the same as it would be if I used the previous equation. But now the other variable I have here is the distance from 0, the central fringe to the 3rd fringe. That's X. You can only use this formula in very specific and certain circumstances, and they've really started to test that on the diploma for a couple reasons. One, the textbook does it completely wrong. So do not read anything in the textbook about diffraction and interference, because it doesn't talk about this at all, and it doesn't address this problem at all. And then on top of that, it wasn't until about the last 4 years that teachers actually started teaching the small angle approximation. So they started putting it on the diploma. So they will test to see whether you're doing this, you're using these formulas correctly. So you can only use it when the angle is less than 10 degrees. So when that theta is less than 10 degrees. So what that means is you have to test that first. You have to find the angle first before you can judge whether you can use that formula. So you have to make that triangle where you have the distance between the screens and the distance from the central fringe to the fringe that you're talking about. And then you have to find that angle in there using tan. So inverse tan is going to be X over L. And so then if you get a number less than 10, like an angle measured less than 10, then you can use this formula. But what I think is if you're going to go through the trouble of finding the angle, you might as well then go back and use the easier formula. You might as well go back and use this formula because you have the angle now. Then you don't have to mess around with whether you're getting them in the right spot or not. So basically, when you get a question that isn't asking you to find the angle, nor does it give you the angle, you have to do this first to make sure that you can use that formula. But if you're going to do this and find the angle, you might as well use the angle formula because it's a little bit simpler to use. Okay. A pair of screens are placed 13.7 meters apart, so that's L. A third fringe, so that's n equals 3, is seen on the screen 2.50 centimeters from the central fringe, so that's x. If the slits were cut at 0.0960 centimeters apart, determine the wavelength of this light, so that's d. So we have a few units we have to convert. L is okay because it's in meters. N is okay, it doesn't have any units. The distance from the screen, the distance from the central fringe to the third fringe is 2.50 centimeters, so 0.0250 meters. And then D, again, it's in centimeters, so 0.0960 times 10 to the negative 2 meters. And we want to find lambda. So you always have to check your angle first. So we have a rectangle here, or sorry, triangle. That's L, and this is X. So this is 13.7 meters, and X is 0.0250 meters. Okay. And that's the angle we want to find there. Now I can actually tell from looking at that, because in order for that to be a very large angle, like because there's a significant difference between 0.0250 meters and 13.7 meters, that angle is going to be tiny. So you think about that, 13.7 meters, that's like maybe the size of this classroom, maybe a little bit bigger, and then 2.5 centimeters is about that big. So the triangle it makes is going to be very puny. But we're going to carry through the checking anyway. So theta is equal to inverse tan of 0.0250 meters divided by 13.7 meters. Which is going to give you a super, super tiny angle. Okay, and these are the only calculations we do where you're not really going to be immediately aware of whether you're in the wrong mode, right? Because usually if you're in radian mode, you get weird answers like that where you used to get kind of bigger angles. But in these questions, you're going to get fairly small angles. So you need to be really, really careful with that degree versus radian mode. So that's definitely less than 10 degrees. Okay. So that means we can use lambda equals xd over nl. So x is 0.0250 meters. D is 0.0960 times 10 to the negative 2 meters. N is 3, and L is 13.7 meters. So one thing you want to be careful of here is using brackets. You especially need the brackets on the bottom. And if you chose instead to use this formula, which you can because you have your angle, you would get the exact same answer. You're going to get the exact same answer. So you get 5.84 times 10 to the negative 7 meters, or you can write that as 584 nanometers. So that's what you would get down here. If this angle was greater than 10 degrees and you still use this formula, then these two numbers will be different. Okay? And I think I'm going to be able to illustrate that in the next example. It's 9. It's 9, but yeah, it's because I'm moving. Yeah, because I'm writing as 584 instead of 5.84. Okay. Questions so far? Yes, I think so. I don't have I'm kind of bad because I'm telling you guys have to memorize it. I don't have to memorize it. And I have such a, I don't really think, I think there's a benefit to memorizing stuff, but it's so out of touch with reality in terms of the stuff you have at your fingertips and access stuff. So I've done a lot of reading, and there's a push in the States, we have open book tests and stuff like that. And they're just basically saying, tests should be open phone. It should be open anything, because that ability to find information when you need it is a much greater skill than being able to memorize a formula. So I find that interesting. I think there's going to be a lot of shifts in education in the next 20 years in terms of that. Like I'm thinking if I've got a doctor operating on me, I think I would like to know that maybe the night before he looked through his manual or not manual, but something to check, to kind of refresh himself on stuff, as opposed to just, yeah, well, I remember that from 10 years ago, so I'm just going to kind of go in. That's a bad example, but okay. Yeah. Well, the thing in that is you have to be able to discern if the information you're getting is correct. Right? Like if you're getting everything from Wikipedia, it's probably not. Right? So that's part of the thing. Oh, I think so too. It's like when I was in high school, we had to memorize it. Probably the dumbest thing ever I've ever had to memorize. Yep. Well, I mean, yeah, that's kind of a bad example, but what I'm saying is I wouldn't want him to just assume he remembered everything. That's kind of what I'm talking about. Yeah, and that's the doctor thing's a bad example. I haven't come up with a different example, but it's more just that, once you leave school, you never really are in a situation where you have to do a lot of memorizing. You always have books to look at. And my father-in-law was a calculus professor. And this whole notion of starting a problem on the board and solving it in front of the class, they would never do that in calculus back then. Because you might fill 2 boards with calculations and realize you made a mistake back here, which means everything in the middle is garbage. And that's a very embarrassing thing and a hard thing for teachers to get through. So I find that, so they were always using books, right, to figure out what they're doing. And that's like all of the stuff you do in calculus, like all the integrals and derivatives are all in books. You don't memorize them. So, anyway, okay. Diffraction grating is located 1.5 meters from a screen, so that's L. A second order maximum is located 35 centimeters from the central fringe, so X is 0.35 meters. Maximum just means antinode or fringe. Minimum is the space in between. What is the distance between the slits on the diffraction grating? So we're looking for D. If the wavelength of light is 409 nanometers. So we want to check our angle first. Okay, so we have 1.5 for L and 0.35 for X. So theta is equal to inverse tan of 0.35 meters over 1.5 meters. So you do get an angle over 10. Since that's greater than 10, that means you can't use lambda equals xd over nl. Okay, so that's forbidden formula this time. So we have to use this one. So d is equal to lambda times n divided by sine theta. So 409 times 10 to the negative 9 meters times 2 divided by sine of the angle we found there, 13.13. Yeah.
If the first formula could be used for pretty much any angle, then what is the point of having that second formula around?
Because sometimes if you're solving for X or L, right, you need that formula, okay? And then what you actually need to know in the curriculum is that small angle approximation. So, but that's like, because this formula doesn't have x or l in it, so you can't solve for those variables. So this gives me 3.59988 and so on times 10 to the negative 6, which I'll simplify to 3.6 times 10 to the negative 6 meters. If we wanted to actually see what happened when we use the other one, so D is equal to lambda times n times L divided by x. Then what we get here is 3.506 times 10 to the negative 6 meters. Not a huge difference. It's off by 1/10 of a decimal place, but that's significant enough. And this would be a numerical response question on the diploma where 3.6 would be correct and 3.5 would be incorrect, because they can tell if you have 3.5, you use the wrong formula. Okay, I'm not going to get to that last example. The one thing I want to do, like, we'll go through the last example because I'm going to run out of time. But it's this. When you're given D as a certain number of lines per a distance, okay? I just want to show you how to convert that in case you encounter it in some problems at the beginning of the assignment before we go over this on Monday. To get that into meters, we have to flip this basically. And we're going to write 1 millimeter in meters. So that's 1 times 10 to the negative 3 meters divided by 600 is what you would do there. So that would give you 1.667 times 10 to the negative 6 meters. So 237 to 243, 1 to 17. Oh, 237. Okay, we're going to do one example, finish that example, and I'm hoping to do a lab on Monday. If you've done any of the questions, you could have done up to 1 to 15 on your unit assignment. If you have that done and want that marked, you can hand that back. We'll have time on Monday to work on the unit assignment for these questions.
So So basically the point is to say that they still don't know if light's a particle or which.
Oh, no, we do know, it's both.
It's both.
It's both. In certain circumstances, it acts like a wave, and in certain circumstances, it acts like
So it's really neither but both.
Yeah. Yeah.
Very.
I don't know, I'm worried about
Almost died the other day again.
You're still sick, eh? Still same thing?
Yeah.
It's still high though, right?
Yes.
Not low?
Still ridiculous.
It's taking you a long time to recover from it. Okay, oh, look at the, over and look at the Christmas light.
Why you got snowmen?
Yeah, it's the same idea.
Like making weird things.
What's your day when you've been gone?
Yeah, it sucks.
It's tough. I think a lot of people just don't understand how difficult it is to actually, well, just to manage stuff and the things that can go wrong, how much it affects your life.
Everything goes wrong.
Oh, yeah.
That's how I feel.
Yeah, oh, yeah, yeah. We've had disaster situations where my husband put his daytime insulin, his hemoglobin insulin, and his nighttime in. So he took his supper insulin and then his nighttime insulin that was also fasting. I woke up and he was seizing. He was having a seizure. And when I actually tested his blood sugar, which, like, he shouldn't have actually been talking, but the thing is the seizure kind of forced his body to produce a little bit of sugar, so then he was actually lucid and talking to me when the paramedics showed up. But that was, and so then he switched and got it so that he was on a nighttime insulin where the vials would not fit in the daytime insulin pen, like two totally different vials. Yeah. Yeah.
Does he have the old school pens, or does he have like newer age?
He's not ones like the ones that you want, ones that, like you have. He used to have really tiny ones, like about the size of a highlighter.
Oh, wow.
And the vials are totally different. But when I first met him, he was still using syringes.
It's just kind of how's your long weekend? I don't talk to you long. Exciting? Did you do anything fun or exciting? That's counting on people's party.
Oh, it's Friday. None of that came around later. Hey, you're here on time.
I took the bus.
Well, that's good.
But
Hey.
I was just on the bus.
Sleep on the bus.
Well, this isn't even